please respond in chat box. And it's a humble request from my end. Please mute all of you from your end. And whatever the things, if you have, we have a question and answer session at the end of the at the end of this at the end of the presentation and the case studies. So you would like to ask me the questions, whatever you have. So I guess all of you can see my screen. It is visible. So first of all, I introduce myself. My name is Jayesh Gupta, and I'm working here from the last 3 years. And I did my masters in nuclear engineering. And so today I'm going to present a tool called Flownex, and the Flownex is a 1D CFD code. And I just explain like what is the 1D CFD code and how this Flownex is built. Yeah. So Flownex is basically a South African code. It started developing in 1982 with the collaboration of the Johannesburg University and the ASCOM industry. Now, the Johannesburg University is a very well-known education institute, and the ASCOM Industries is like the NTPC, or the, you can say, nuclear industry of the India. As this tool is developed in a nuclear industry, this tool has a nuclear module and a nuclear capability to solve the problems. Okay. Now, Flownex is basically a 1D CFD code, and it is widely used for a system, subsystem, and the component level of analysis. Now, in this tool, both the solvers are there. One is a flow-based solver, and the another one is an energy-based solvers. Both the solvers are coupled very well, and these solvers are worked in both the environment, like a steady-state environment as well as the transient environment. Now, apart from that, this Flownex tool has a different modules or different physics availability, like digital control systems and the electrical modules. It's going to happen with the digital control system, the electrical module. Suppose that if you want to create a digital twin, which is very widely used in the industry right now, and the people wants to control everything through a single screen. So that moment, that kind of a simulation, if you want to create, that moment you need the digital control system library as well as the electrical library to understand the real system behaviors. So whenever I'm talking about the real system behavior, that moment you need how your PID is going to lag. Suppose it is lagging are there, then that lag should be in your software also is reflected. If it is that kind of a things, we to create that kind of a environment, we need the digital control systems and the electrical systems. But this is not the limitation of this tool. But suppose that if you want to create your own libraries, or if you want to create your own physics, so that kind of things also you can create. Now, unlikely a 3D CFD course, you don't need to create your geometries, and you don't need to waste, means like you don't need to spend more time on the creating mashing. So in this code, we just need to drag and drop the particular geometries from the master database, and that geometry you can drag and drop onto the canvas on a working window. And the likewise, you can see on the right hand side window, there's one pipe is there, one pump is there, and one boundary conditions are there. I'm getting some disturbance. Can you please mute yourself from your end? Please, hello. Please mute yourself. Okay. So as you can see on the right hand side, there is a pipe element is there, then the pump element is there, and one more pipe is there. So likewise, you need to drag and drop the particular component or base component from the master database, and you can create your network, and you can assign the inputs to that particular component as well as to the boundary condition, and you can solve your systems. Now suppose that if you wish, like I'm looking for a geometry which is not available in the master database, or which is not inbuilt available. So what we can do, we can create the geometries by using a scripts. So this tool has a scripting phenomena also available is there. and the script I can create the geometry in a parametric way, and the way you want to create a geometry, that geometry I can create. Okay, so that is the facilities available in this tool. Now how this tool is going to work in a backend, so I'm going to explain like what kind of algorithm is going to use. So first of all, this tool has a discretization method based on the finite volume method, and it is works on the IPCM algorithm. IPCM stands for the implicit pressure correction method, and in this method what is going to happen, suppose that you can create your network, and as you can assign the inputs and the boundary conditions. So according to your boundary condition, it is trying to assume the pressure at each and every node, and after that it is going to solve the mass and momentum, and once this is mass and momentum is converged, then you are going to convert the energy. So this is the way it is going to solve your networks. Now what is going to happen, like when you are going to use a 3D CFD codes and a 1D CFD codes. So 1D CFD codes is like used when your flow is flowing into one direction. Whenever your flow is flowing into three direction, that moment you are use a 3D CFD code. So I can give you example of that. Like suppose that if you have a refrigeration cycle, the complete refrigeration cycle is working on the complete unit like vapor compression cycles. So in that vapor compression cycle, the complete thing is the flow is flowing into one direction. But whenever it comes to absorber and evaporator end, and at that moment, like suppose that if it's going to a room environment or a complete duct environment, that moment you need to use a 3D CFD code to understand whether there is a stagnation point or not. So what kind of things it is going to handle? The fluid capabilities like incompressible fluid, compressible fluid, two-phase fluids, incondensable slurries, gas mixtures, heat transfer, mechanical system, control system, electrical systems. You can use the apart from these systems, if you have a MATLAB code or if you have Python code or if you have Fortran code, so that code also I am going to link. And suppose that if you want to introduce your fluid library, you can introduce your own fluid libraries, and apart from that you can import the fluid from the NIST database, that is called the NIST reference prop. As I mentioned, it has a complete steady state and the transient capabilities, and as you can see on the right hand side one graph is there. This graph is nothing but a surge analysis graph, and in this graph I am going to plot how the pressure is going to vary with respect to a time in the event of a sudden closure of your valves. So how it is going to prolong or how it is going to wave. So it is going to form a wave velocities, and it is going to create a maximum and the minimum pressure inside your complete domain, and you need to understand after what time it is going to diminish. So that kind of a things you can easily do with this tool. This is the GUI, and just taking more 2 minutes, and after that we are going to start working on one particular problem. And what the different things available in the Flownex apart from the other tools. So it has a widest combination available for the flow and a heat transfer kind of a components, which can be worked in both environment like steady state and the dynamic simulations. Then you can easy to integrate this tool with the ANSYS Fluent, ANSYS Structures, ANSYS CFX, LabVIEW, EASE, MapCAD, OPC, AutoCAD, MATLAB, and the Python and the Fortran. Whatever the tool you have available, I can directly link with this tool, and it has a two-way coupling available. So we have the inbuilt APIs are there. That API is going to call with your particular software, and we can work together. So these are the users in India right now for the Flownex. So Flownex used in India, IGCAR, Kalpakam. It is the stand for IGCAR. It's like a Indira Gandhi Center for Atomic Research Center. It's a DAE Department of Atomic Energy, India. Then BHEL, Bangalore it is using. Then IISc Bangalore is using for extensively research on a supercritical CO2 cycle, and that cycle we are going to develop. We are going to make a digital twin as well as a heat exchanger modeling. And then IIT Madras is used for turbo machinery applications. IIT Bombay is going to collaborate with the BARC in Bombay, and they have performed the simulations on natural circulations, so NC problems. Then IIT Kharagpur is widely used for the cryogenic fields, so they are using for the cryogenic domain like surge analysis, and like how your pressure and temperature is going to vary with respect to your time. Suppose if you have closed tanks and that is going to a space. Then JNTU Hyderabad, JNTU Kakinada, BITS Goa, BITS Pilani, GC Kozhikode, and CU Gulbarga, these also are users. and this is a model matrix. So I just start with some particular problem. So the problem statement is like that: there are the three vessels are there. Consider tank A, tank B, and tank C. The working medium is a air, and all the three tanks has a different volume and as well as the different what is called pressures. They have the this is a closed container. They have the different pressure and different volumes are there. Initially, the entire system has a three tanks, two pipes, and two valves are there. So this both the valves are initially closed. And suppose that if I want to open the valve after 1 second, then I just want to understand after what time this tank has a equalized pressure and how much means like what is the equalization pressure value and how much time it will take to reach the equalization pressure. So this is the things I want to solve in a Flownex. So I'm start modeling in a Flownex. Please let me know if you have any questions up to now. So I will start modeling in a Flownex. So I already open a Flownex environment. First of all, I just introduce what is a Flownex environment. So in the top of the side, you are getting the different toolbars are available. So basically, this is for the configurations for a particular problem, as well as to solve a particular problems like I want to solve a steady state, or I want to run transient simulations, or I want to run a designer or optimizer or a sensitivity analysis. So all these kind of facilities available on the top of the window. On the right hand side of the window, you are getting the heart of the tool. So it has a component libraries available are there. There are the flow solvers libraries are there, and you can see the
Just for a moment, is Flownex available in MATLAB?
MATLAB means what?
MATLAB software.
MATLAB software is available with this, or MATLAB software can link with this software.
Yes, I am. That MATLAB software, can MATLAB software be linked with this software, or it is a separate software completely?
MATLAB is some completely different software, and
No,
suppose that if
can
you have
these two be
MATLAB
linked?
link means
Can these two be linked?
yeah,
Means
yeah, it is
if I
like
have a
yeah, co-simulate. Yeah, yeah, I understood. It is co-simulate with the ANSYS, sorry, with the MATLAB.
okay. So if I have a
Yeah,
MATLAB software, I can run Flownex software also. There I can do this type
yeah,
of.
you need the Flownex software available with you, and after that you can co-simulate with the MATLABs.
Okay, okay,
Yeah,
okay. Thank you.
yeah. Thank you so much. So it has a different heat exchangers models like bulk air cooler, cooling tower, evaporators, fin tube heat exchangers, normal split heat exchangers, shallow tube heat exchangers. But this is not the limitations of these heat exchangers. You can make the heat exchangers by using a simple fundamental things like conjugate heat transfer, conduction, convection, cross conductions, distributed heat source, film convection, fluid radiations, jet impeachment convection, surface radiation. So all these are the inbuilt tool available. But suppose if you want to if you want to introduce your own convection correlation models, then you can create your own convection correlation models as well. Then it has a rotating components available in this like vortex, custom vortex, force vortex, free vortex, labyrinth seals, then rotating annular gap or rotating channels, rotating nozzles, rotor cavity, rotor stator cavity. If you are working in a gas turbine domain and if you want to simulate a secondary air analysis for the gas turbines, that moment you can use extensively use these libraries. And again, these libraries also available in both domain like steady state as well as in the transient simulations. So I'm just start with our particular problem. I just again repeat the problem statement. There are the three tanks are there. All the three tanks have a different volumes and they all have a different total pressures. And all the complete system is connected to the pipes and the valves. Initially, both the valves are closed. Once I open the valve, then I want to see how much time the system will take to normalize or equalizations and what is the equalized pressure for that particular problem. So I'm going to start the modeling. So please be with me. So first of all, I'm going to a component library. In that, I'm going to expand a containers. In that container, I have a reservoir kind of a component. So I am going to drag and drop that reservoir onto the canvas. And after that, I'm going to connect one pipe with this. So I'm going to connect one more pipe over there. And then there is one wall is there. So I'm using a restrictor. Restrictor is the discharge coefficient. And after that, I'm going to again connect one more reservoir, and then I'm going to connect a wall, and after that the wall I'm going to connect one more pipe, and after this pipe I'm going to connect with one reservoir. And as you can see, there are the identifiers are there, and this identifiers looks messy. So I'm going to deselect the identifier. It is going to be a clear. Then I'm going to assign a three boundary conditions to each and every what is called tank. So I'm assigning the three boundary conditions to each and every tank. And now I'm start giving the datas. So I have the datas available in this. So as you can see, the initial air pressures for the three tanks are 675, 550 and 750, and it has the unit of kilopascal. So I'm going to assign the boundaries. Like I just double click onto the boundary condition. As you can see, there's a pressure boundary condition is there. Initially it is not specified. If I'm going to double click on that, that is asked fixed on the user total value. I'm going to say I want to fix it, and the value for this is a 675 kilopascal. Same way I'm going to assign for the second one. So it is going to 550 kilopascal, and for the third one I'm going to assign the 750 kilopascal. I'm going to see what is the temperatures. The temperatures are the 40 degree centigrade is the same, and the vessel volumes are 40 meter cube, sorry 50 meter cube, 40 meter cube and 30 meter cube. I'm going to make first of all the temperature. So what I can do now, I can multi-select all these three boundary conditions, and simultaneously I'm going to assign the boundary condition to each of them, and I'm going to assign a 40 degree centigrade. So this kind of facets are solved, and you can see whenever you are assigning some particular boundary conditions, that moment you are getting the initials near to your boundary condition component. So now I have assigned a pressure temperature, pressure temperatures, boundary conditions to this boundaries condition to these boundaries to this component. Then I have something called a tanks. In that tank, I'm going to assign a volume. So initial the volume for 50 meter cube, then it has a volume of a 40 meter cube, and then it has a volume of a 30 meter cube. Please mute yourself from your end. Now I just need to assign a pipe data. So as you can see, both the pipes has a length of 1 meter, and the roughness is a 40 micrometer, and the both has a different diameters. One has a 0.05 meter and another one has a 0.025. So what I am going to do, I am just going to multi-select both of them the way I'm going to I have done for the boundary conditions. Then I'm going to assign a 1 meter as a length. Roughness I am going to assign a 40 micrometer. One more I'm going to check, and it has the whatever the roughness I am going to assign. That roughness is a primary loss in my system, but as this pipe is connected to the tank with a sharp edge, so it has a sharp edge, entry loss is also happening, which is a secondary loss. So I'm going to assign a sharp edge entry loss coefficient 0.5 for the both the pipes. So I'm going to assign the K forward value, and that is the 0.5. And I have to assign the different pipe diameter. So first pipe has a 0.05 meter, and the second pipe has a diameter of 0.025. So I can say like it's a half of the first pipe diameter. And now I'm going to assign the values to my walls. So initially the walls, I'm multi-select both the walls, and initially the walls cross-sectional option is area. Instead of that, I'm making a diameter, and in the both the diameters are different because in a problem statement it's mentioned like that whenever the valve is fully open, it has the same diameter as the bore diameter of the connecting pipe. So I'm going to assign the later on, and for the demo session, I am assigning a discharge coefficient as a 1. That is not ideal. It is generally lies if it's a very good wall. That is maximum is going to up to 0.8 discharge coefficient. Okay, and this I'm going to specify the opening, and I made the opening 0 because initially both the walls are closed. Now I'm going to assign the diameter to respective wall. So first wall has a 0.05 meter diameter, and the second wall has a 0.025 meter diameter. Now what I'm going to do, my steady state simulations is prepared, and I'm going to solve the steady state. So I am getting the error. Now you can see in the error log, there I am getting an error. And what I need to do, I just need to open a single, total 9 errors are there. I am opening a first error, and you can read the error, then you can easily understand what is going to say. So it's mentioned like fluid is not assigned. Right click on any Flownex component on the drawing canvas and select the assigned fluid from the context menu to select the fluid flow for the circuit. So up to now I am not assigning any fluid. So that's why I am getting an error. So whenever you are forget something, the solver itself is going to tell what you need to do and how you need to do. So this is the beauty of this software. It is not mentioning only the error, but it's also telling where you can resolve this error also. So what I'm going to do, I am just selecting any component from the Flownex network and right click over there, and there is a assign fluid, what is called tab is there, and if I'm clicking, the new fluid assignment window will appear. Over there I'm going to assign a pure fluid, and there's a gases are there, and the air is an inbuilt domain is there, inbuilt fluid is there, so I'm going to assign an air. And now I'm going to run a solid, just like I'm going to run a solid steady state. Then I'm getting the complete convergence, and the solver time will take 0.26 seconds, and it is taking a 12 iterations. Now what I'm going to do, I'm going to check what is the mass flow rate in both the pipe. If I am going to see the mass flow rate in both the pipe, then I can drag and drop that mass flow rate onto the canvas, and as you can see, it is mentioned like 0.0 kilogram per second, 0 kilogram per seconds, because in both the case ball is closed from both sides, so there is no mass flow. Now I'm going to create a transient simulation. So for creating a transient simulation, I need to first of all give the actions, like what is going to happen when I'm going to run a transient simulations. So in our problem statement, it is going to happen both the wall is going to being open. So what I'm going to do, I'm going to select the first wall, and there is a one opening kind of a feature is there. So I'm going to drag and drop that opening into a transient action, and the same way the other dragging and dropping. And I'm going to say after a 1 second, my both the walls should be fully open. So I just made is a 1 value, and whenever I'm going to perform this kind of a simulation, that moment this boundary conditions which I'm going to assign over the tanks, that boundary conditions is going to maintain the particular values of temperature and pressure forcefully, because that is the meaning of the boundary conditions. So what I need to do, I need to what is called, I need to remove these boundary conditions. Okay, when I'm running a transient simulation. So for making that, I'm not removing, but I'm made as a disable. So I'm going to disable the boundary conditions of each of the tanks. Okay, so pressure boundary condition of first tank and the temperature boundary condition of the second tank. The same way, the pressure boundary condition of a first tank and the temperature boundary condition of a second tank, and the third pressure boundary condition and the temperature boundary conditions I'm going to make. And as you can see in this window, the value itself, it is staying fixed on the total user value. So instead of that, I am making not specified, not specified, not specified, not specified, not specified, and not specified. That means I made my boundary condition disables. So my transient actions are ready. Now I'm going to assign up to what time I want to run and what should be a time step size for this particular simulations. So I'm going to click on the scheduler. In that scheduler, what is going to happen? It has a both kind of a feature available. Like I can give a time step size manually also, as well as the simulation based also. So right now I'm using a manual based. So I'm taking a time step size of 100 millisecond, and the simulation end time initially is a run indefinite. Instead of that, I am making a specify the end time, and I'm running for a 150 second, and I want to see like within a 150 second I'm getting equalized pressure or not. So this is my overview, and I'm taking a snap for the steady state. I explain when I'm using a snap. Right now I'm just creating a snap. So I just made this snap called as a steady state, and I already load that snap. So I'm going to click on the solve steady state, and now I want to plot the total pressure of the each tank. How this total pressure of each tank is going to vary, that I want to see. So I'm going to create a one graph, a line graph, and that line graph I'm going to give the name as a sorry, pressure variation. And in this line graph, I need to drag and drop the total pressure of a tank 1, which is 675. Then second has a 550, and the third has a 750. And now I'm going to edit the properties of a graph. So what I'm going to make, the x-axis has an auto scale, and you can see the scaling is 0 to 10. Instead of that, I'm making 150 because I want to plot for a 150 seconds. And then in a, you can see the x-axis has a title of a time, and it has a unit also. So I make the same way. For the y-axis, it has a total pressure, and it has the unit group of a pressure stress. Why I'm creating right now, because you can directly export your graph from here and you can use for a research articles. So you don't need to worry about creating that things for a what is called in Excel and then formatting again. So it is going to reduce your formatting things. And here I am going to make a history recording for a 150 seconds, and each what is called 0.1 second it is going to record the simulation. So after that I am able to take the values in a form of a Excel. So that is also possible. And now I'm going to make the line items changing. In the first line items has the initial as a tank A total pressure, and the width of the lines are 2, and this line is a solid line. The second one has a tank B, and it has the width of 2. I can take orange, and it is a width of 2, and I'm going to take dash dot as a line formatting, and here I'm going to take a tank C, and I'm going to make it the width of 2, and the line is only dash. Okay, and I just click on an OK button, so you can see the dash dot dash and the solid line is there. Now I just need to run a transient simulations. So I'm going to run a transient simulation. I'm going to take both the openings over here, so you can easily able to understand whether this wall is going to open or not. So I click on a run button. As you can see, the wall is open, mass flow is also varying, and all the boundary conditions are what is called vanished. And you can see how fast the simulation is going to happen. And yeah, so I am getting the equalization pressures of 651.79 kilopascal, and it will take 107 seconds to reach. I just run one more time the same scenario. So what is going to happen after running a transient scenario? Now my openings will change, okay, as well as my boundary conditions also vanished. Suppose that I want to come back to a steady state. So that moment, what is going to happen? I have to manually change the openings of both the walls, and I want to manually change, or I want to assign one more time the boundary conditions to each boundary condition element or to each tank. So that is become tedious. This is a simple network, but suppose that if you are working on a huge network, So that moment it is not going to work out. So that's why we need to create a snap when the steady state simulations are performed. So what is going to happen with the snaps? That snaps capture all the component variables and the properties in that. And when I'm going to load, so it is written back me to that state. You can see all the boundary conditions assigned now. Openings becomes 0. And now I'm just going to run one more time this simulation, and you can see the how fast the simulations are there. So like as the sir told, like you want to create your labs. Okay, so practical labs are there available in the colleges. But whenever you are performing that particular, means like instead of making that lab available in this COVID-19 situation, so you can use software-based labs. In that software-based lab, you can create the same apparatus, and you can tell your students to perform, and then they can perform and they can record each and every parameters. So how they are going to vary. So this is a good thing in that. And as the market is going to driven, like nowadays people are more what is called, means like industry requires the more analyst, CFD analysis, and the thermal engineers. So become a good up career in the field of a CFD, in the field of a thermal engineer. So you need to understand the 1D CFD course rather than, it's like a basic fundamentals things. Then you can move to your 3D CFD course, and once you have the both couplings available with you, then you will become a good analyst in your market. Okay. So this is the first case study. Please let me know if you have any questions up to now. Any questions from your end in behalf of Flownex or in behalf of this particular case study? Okay, so you understood like how easy it is.
Sir, somebody
Okay.
else is sharing his screen. Can you
Okay.
please stop that?
Someone want to share his screen?
No, somebody else is sharing his screen, so your screen was not visible.
I have stopped my screen. I don't
Yeah, you
know.
can share now.
Hello.
Okay. Yeah, hello.
Good morning, sir.
Yeah, good morning.
For the presentation, among the doubts, can we find out the individual fluid particles properties like pressure, temperature at individual fluid particles, like whatever is
Yeah, you
flowing?
can. Yeah, you can.
Okay, like if we have a Bernoulli's equation which is to be derived, and then at each and every point, can we find out what is the pressure and the temperature, or what is the velocity like at each and
Yes,
every
yes,
point?
yes. Yes,
That
yes, you
simulation is
can.
possible. Okay, thank you
Yeah,
so much.
like
May I,
okay. Yeah.
may I know your good name, ma'am?
I'm J. Siddharth Yadav from Raghu Engineering College,
Okay.
Vishakhapatnam, sir.
Okay, sir.
Thank you.
Yeah.
Yes, thank you.
Hope you can see my screen now.
Yes, sir, it is
Is it
visible, sir.
okay? Okay. Yeah. So like in the tank is there. So tank has a 675. Okay. Then it is not a steady state. Suppose if I'm going to make a half opening, you are able to understand what I'm trying to say. And I make a half opening. So you can see it has a 675 kilopascal now. In a pipe, it is 665.04, and the temperature also decrease, and the mass flow rate is a 1.105 kilogram per second. And in the wall the velocity, you can see what's the velocity near the wall, the Mach number also you can see, and also you can see whether your flow is choked or not. So you can see whether it's like choking phenomena. So it is widely used in a compressible flows, and whenever you're working in a city nozzles, so people are more working like GTREs are there, ISRO is there, so that people are more worried about whether the flow is being choked or not. So that kind of a things also available in this tool. So yeah, the answer of your question is, yeah, you can able to see each and every point how your pressure and temperature is going to change according to your locations. Okay, so now I'm going to move to a second case study. So this case study is it's on a uh, Rankine cycle. This Rankine cycle is a full-fledged Rankine cycle. So I'm going to create I'm just going to open that.
Sir, I just want to make one announcement.
Yeah.
So at the end of the session, we are going to share one a link for the feedbacks. So according to those feedback name and your organization name, e-certificates will be generated. So be attentive till the end of the session. At the end, we'll share the link, and those who fill the feedback properly with proper name, whatever name you want on the certificate or your organization name on the certificate, according to that feedback submission, will generate the certificate. So at the end, we'll share the link with you. Okay, in the chat box possibly, or you can also visit on your on our website after that, after the session. Okay. So continue, Jay sir. Please share your
Yeah.
screen.
Okay. 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 It's opening.
Jay sir,
Yeah. I'm
Jay sir,
opening my. Yeah.
there are some questions in the chat box also. Please see those also. Okay.
Yeah.
Somebody has asked, can we study fluid properties, sir, like founding, boundary
Yeah.
layer thickness, or slip length?
Uh, Give me a second. I'm not able to see my chat box here. Can you just say hi in the chat box?
Yeah, a lot of comments are there already.
Yeah. Give me a second. I just open settings. Yeah, I got it. Give me a
Okay.
second. Yeah, I'll just start giving. Two slides are visible. Please check. One of the faculties isn't mute, so didn't you stop screen sharing. Those who are going okay. Yes, but due to network issue we missed during that. Please send the link
Go
to
below
this.
that.
Yeah, yeah. Do you have any simulations vapor absorption cycles? We have right now on the vapor compression cycles, but as the way we can create a vapor compression cycle, we can create for the vapor absorption cycle also. Mr. J. Siddharth Yadav. Okay, so yeah, we can create the vapor compression cycles. Queries and questions will be taken at okay. And one more guy will attendees will get the certificates. Okay, yeah, they will get the certificates. Right now they are saying, can we study fluid properties, sir? I like finding boundary layer thickness of a slip length, sir. So Rajshri, this tool is a 1D CFD code, and as the 1D CFD codes does not have the features to solve the boundary layers problems. Okay, so for creating a boundary layer solvers, you need to go with the 3D CFD codes only. Yeah, I guess so. And apart from that, if you want to create a boundary layers, so what I can do, I can make a script over there, and I can write the codes in a MATLAB, and MATLAB I can simulate with Flownex. But again, this is not a viable answer for your question. So I would like to recommend, if you want to work on a boundary layer thickness and you want to see like how your velocity profile generated according to your turbulent flow, and how your piecewise linear profiles will be created, and how much of the mash you are going to perform, and how you are going to appropriate wall functions you are going to apply. So that all the things, either you can create your own solvers in MATLAB, Python, or any other language, or you can use available softwares, or 3D available softwares are there. Okay.
Go below, sir.
Is Yeah, it is allowed user to drive the design of their entire system through simulation if possible. How? See, designs is already available. Suppose that we are working right now with the TC and the Siemens, and they are working on a particular process plant. So process plant design already built by a Siemens. What we are going to do as an analyst, we are going to say whether this design, complete design, will work with the different transient scenarios or not. Suppose that boiler is going to trip, or your turbine is going to trip, or uncertainty is going to happen, like you are close a valve suddenly, then whether that particular design will sustain that particular events or not. So that is going to happen with this. If you want to tell me like what specific design you are looking for, then I can able to answer in that way. But generally, for a complete plant or a system or a subsystems, the design already made, and that design, what we are going to do, we are going to what is called see whether this design will sustain under certain conditions or not. Apart from that, suppose that if you have process parameters available with you, and you want to tell me like I want to create a design for a vapor compression cycle or vapor absorption cycle. So in that manner, yeah, we can create the designs also. We can make the appropriate design with respect to your process variables. So in that case, I need the process variable first of all, like whatever the what is called power consumed by your compressors, whatever the heat transfer is going to happen in condensers, means like what is your design requirement. So once your design requirement is filled, then we can use this tool to create a design as a design tool also. So yeah, you can create this tool. It is important to study the Rankine cycle with the different working fluids or other than water. If we are using the any other fluid, then what is going to happen? Uh, if it is going to create means like other fluid rather than the water, then it's become a Brayton cycle, not a Rankine cycle. So that's why I'm going to say Rankine cycle. Can we design thermofluid? Yes, it can. Yes, we can create the CFD simulations for the receiver tubes also. Okay. Yeah, I'll just answer your all queries. Okay, please commenting in that, and then we are going to I'll answer at the end of the sessions. Okay. So this is the environment. Okay, this is not the thing what I'm. Oh, yeah. So first of all, I'm going to explain a complete HMI of the Rankine cycle. So please let me know whether you are able to see my screen or not. So this is a complete Rankine cycle. This is created by our team in Flownex, and then you can see here one drum is there or a boiler is there, and this boiler you can see it works on 260 standard atmospheric pressure, and it has the enthalpy of 991.355 kilojoule per kilogram, and you can see this much of the mass flow rate is going to flow, and this is the temperature of your boiler. So after the boiler, whatever the steam is created, that steam is going to your turbine. It has a three-stage turbine. It's a modern Rankine cycle. It is not a normal Rankine cycle. And this work we have done for a NTPC. So it is going to your turbine. First stage turbine or HP turbine has a two bleed steams. So we are going to take the bleed outs from the turbine, and from the after that this from the HP turbine it is going to your IP turbine, and IP turbine also has a three stage, and from that three stage we are going to take out the two bleeds, and after the IP turbine it is going to your LP turbine. LP turbine also has a three stages, and from that also we are going to take the bleeds take out from the LP stages. After that, whatever the steam is there, it is going to your condenser. It is cooled down in the condenser, and from that it is that condensate is going to flow through your LP heaters. So these three are the LP heaters are there, and in these three LP heaters, I am going to whatever the bleed is coming from the IP, LP, and the HP. So for that bleed is going to use to heat your condensate water, and then this is there are three heaters are there, LP heaters are there, and after that LP heater is going to your deaerator. In the deaerator, whatever the dissolved oxygens and the gases are there, that we are going to take out from the system, and the pure fluid we are going to flow again to HP heaters. In a HP heaters again, the high temperature bleeds which is coming from the uh, MP turbines or intermediate pressure turbine stages. So initial stages, whatever the bleed is coming, it is going to your LP heaters, and after that is again going to heat up, and then it is going to your boiler. So this is the way we are creating a complete cycle. Now you can see the TS diagram also for this cycle. So you can see this is a TS diagram, and again your there are the first first turbine, then second turbine, then third turbine. It is going to condenser, and means like fourth is the condenser. Then it is going back to your what is called IP term. Sorry, LP heaters. Then it is HP heaters, and this is again going back to from the boiler to a first stage. So this is a complete cycle is there. I'm going to give you the network of the complete cycle. So you can see this is a complete network. What we are going to do. So we have used a two-phase fluid over here, water, and for that the two-phase tanks are there. This is again my boiler. As I mentioned, the my HP turbine has a two stages, and I'm going to take a bleed out of that. So this is a bleed line. This is my HP turbine. From this HP turbine, it is going again back to your my LP turbine, sorry, IP turbines. From that, I am taking the two bleeds. This is a three stage, and again one more LP turbine is there. From the LP turbine, I am going to take the bleeds out. Give me a second.
Yes, sir, you are not audible. You are not audible, yes, sir.
We can't listen you, sir.
Sorry for the interruption. There is some work is going on, so that's why disturbance came. So again, resume the thing. Yeah. So there are the LP turbines are there, and we are going to take out the bleeds from the LP turbines. And as you can see, these bleeds of the LP turbines, it is going to your LP heaters. So these are my LP heaters, and as you can see from these LP heaters also, whatever the bleed is coming, that bleed is going to heat my condensate, and whatever the remaining waters are there from the bleed, that bleed is again going back to my condenser. Okay, so you can see this is a cycle. It is the arrow is going to tell you which direction it is going to flow. So this bleed came, heaten up the condensate, okay, and then whatever the remaining waters are there, it is converted into water. That water we are going to feed back to again condenser. So this is my condenser over here, and after that condenser, it is going to, this is my cooling tower, the simple cooling tower I made, and you can see there's a conjugate heat transfer also there. In that conjugate heat transfer, I'm going to assign a thickness in elemental directions, then thickness in cross direction, then the conduction areas, then convection areas. So I'm assigning all these properties, and after that there's a boiler feed pump is there. You tell to CP to stop that. CP को बोला क्या? ये ऐसा नहीं है. नीचे ना. उसको बोला नीचे वाले को नहीं जाते. Hello. Yeah. So there is one pump is there. This is a boiler feed pump. Okay. In the boiler feed pump, we are going to give a particular curve. So this curve I am going to show you. So as you can see, this is a variable speed pump is there. In that we are going to give a RPMs, and with that RPM I'm going to draw a volume flow with the pressure rise. So this kind of a curve we are assigning over here, and after that, this is again the heat exchangers. So normally in the LP heaters and the HP heaters, there are thousands of tubes are there. In the thousand of tubes, it is going to what is called your your condensate is going to flow. So this is become like a shell and heat exchanger. The complete unit which I'm going to show you here, it becomes a shell and tube heat exchangers. And after that, here it is going to my deaerator model, and from the deaerator again I'm going to pump it out, and this water is again going to back to my boiler, and whatever the bleed is coming, you can see the bleed is coming to your LP heater. These two LP heaters are there, and from sorry HP heaters are there, and whatever the water from the bleed, it is being fed to your deaerator, and again back to here. So what I'm going to do, I just click a solve steady state for this cycle. Okay, so maybe you understood how much time it will take to create a huge sample. So as you can see, it is solved, and this take 0.90 seconds, not even a 1 second, and 46 iterations it is take. And if I'm going to see what is the power output of this cycle, so you can see we have the 660 megawatt. So it's a critical boiler, critical power plant, supercritical power plant. Sorry. So 660 megawatt we are getting as a power. And what I'm going to do, I'm running one transient scenario. This transient scenario will tell like if I'm going to change my is design isentropic efficiency from 93 to 0.7. Will you please mute yourself? Please mute yourself. Yeah. So I'm going to make the my design isentropic efficiency of a first turbine from 93 to zero point 0.7. Then I just want to see how my power is going to change. So I already made a scenario like that, and yeah, it's fine. Steady state already loaded, and we have solved the steady state. And I can go to configuration tab, action setups. Yeah, it's true. And I'm going to run a transient scenario. So as you can see how fast it is going to create a transient scenarios also. So you can see time step size is a very low. I just need to check. Yeah, it's very low time step size. It's like 10 milliseconds. And as you can see,